Okay. So we have been having discussions about neural networks off and on, right? The last time we had a discussion about ANNs was when we did perceptrons, right? So basically, so the whole class of solution methods which are lumped under ANNs or artificial neural networks were primarily inspired by trying to emulate the brain architecture, right. Yeah, so then after a while the field split into two, right. One class of researchers who are looking at neural networks as just computing elements, right, trying to interpret it in terms of linear algebra, right, and functional analysis and other mathematical tools, and then trying to understand what computing these artificial elements were doing, and others who are still trying to make the neural models biologically relevant, right. So now the communities have become fairly divergent, right. So there are this set of people, neuroscience people who are trying to build computational models of the brain, right, and then there are machine learning people who just use neural architectures without worrying anything about biological relevance, right. So yeah, so we will take the latter approach, right. So we will not be looking too much about the biological relevance of the neural networks. We will just try to understand it in terms of computing, right. So do people, have everyone seen a neuron, synapse, dendrites, all those pictures? So you don't have to really tax my drawing skills, right. So I will not draw anything on the board about the neurons, right. So the whole idea behind all these biological neurons is that it's pulling in inputs from a variety of other neurons, right, and some computation goes on within the neuron, and as a result of this it might actually fire, right, in which case it will cause another input to be activated for yet another neuron, right, or a set of other neurons depending on who they are connected to. Then these neurons are all connected in a very complex networks, and even though it is a very simple computing element, each neuron can be thought of as a very simple computing element, the fact that they are connected together in a large network allows them to do all kinds of cool things, right. I mean, if you really want to know what a neural network can accomplish, just stop and think what you can do, right. So one of the earliest models of a neuron was the Macula Pritts model, right. So which is a very simple model. So it essentially it has a summation unit, right. So it has a set of inputs, right, and then it has a set of inhibitory signals, right. Okay. Right, so it has a set of inputs, right, and a set of inhibitory signals. But we are talking about artificial neural networks, and I started explaining the Macula Pritts model. So you have a simple unit which has p inputs, right, and then it also has k inhibitory inputs, right. So what does this neuron do is essentially it adds up these k inputs, right, and if they exceed a certain threshold, right, some threshold theta, okay, then it will output a 1. If it is below a threshold theta, it will output a -1 or a 0 depending on how you are encoding it, right. and the inputs were all considered either to be ones or minus ones or zeros depending on how we encode it, right. What are these inhibitory inputs for? If any one of these inhibitory inputs was 1, there was no output. No output, no output meaning 0, okay, yeah. If any one of these inhibitory outputs is inputs is 1, then there will be the output will be minus 1, okay, or 0 depending on how you are encoding it again, right. So that is the basic Macula-Pritts model, but then just to give you the historic perception, right, and then what happened, people modified this, okay, to propose the perceptron, right. So if you think about what the perceptron does, right, it is essentially saying that right. So instead of doing x1 to xp and adding it up, I am going to multiply it by beta 1 to beta p. So x1 beta 1 plus x2 beta 2 plus x3 beta 3 and so on and so forth. Now if this entire thing is greater than a threshold, okay, I will output a plus 1, right. If the entire thing is lesser than a threshold, I will output a minus 1. So what is the threshold? Beta naught, right. So another way of doing it is to actually add yet another input, label that beta naught, I mean weigh that as beta naught and put a 1 and then, right, okay. Right. So you could think of it that way, right. So usually it is written without the minus sign, right, that essentially means beta naught will be a negative quantity, okay, right. So this is essentially what our perceptron was, right. So you can see it is very closely related to the original Macula-Pritts model, except that there are no inhibitory inputs and the actual inputs are weighted, okay, and we all know how to estimate the parameters of the perceptron, right. How did we get there? We used a gradient descent rule, right. We started with that error function and then we took the derivative. Doesn't quite look like the perceptron rule, does it? Doesn't quite look like the perceptron. What did you do with the perceptron update? So wherever there is a misclassification, what did we do with those? We just added those data points times yi to, so we did essentially did xi yi to the input, right. So we did not do anything like this, right. Did we? No, right. So what we essentially done here is minimize the squared error, right. So there is another way of training perceptrons. Is it something wrong here? What is wrong here?
The main idea was
was the distance from the plane, right? Yeah. So with the perceptron training, so we did something very different from whatever I have done so far. So with perceptron training algorithm, we had a very different objective function that we were optimizing, right? So what were we trying to do? People remember that? You have a quiz like 2 days away. You should have revised all of this by now. Yeah. Minimize the what? Minimize the distance to the hyperplane of the misclassified points, right? And the way you can minimize it is we get a distance of 0, total distance of 0 is when all the points are correctly classified, right? So what we are, the actual objective function we wrote down was we are trying to minimize the distance to the hyperplane of the misclassified points. If you remember, we wrote it only over the misclassified points, right? So in this case what we are doing, we are writing a plain old squared error function, right? But this is actually the squared error there, right? If you think about it, otherwise this is a non-linearity, right? This is the non-linearity, the threshold is a non-linearity, right? I can't just take the derivative of z with respect to x. Does it make sense? I can't take the derivative of z with respect to x because z is a non-linear function of x, right? So z is what? Right, and sine is a non-linear function, it is non-differentiable, so I can't really take the derivative. So in fact what I have written down here is for a slightly modified model of the neuron where the output is taken at this point, okay. The non-linearity is not there. So one way of thinking about this is that is the output, like it is like a straight line, right. So whatever comes as the input, it will be produced as the output, right. So fool yourself for a minute that this line has a slope of 1, okay. So whatever comes as the input will go as the output, right. In that case I can take the derivative of the output with respect to the input. Does it make sense, right. So this is not the perceptron, by the way. So it is sometimes called the what does Adeline stand for? Any guesses? Adaptive, close, linear, adaptive linear. So it is called adaptive linear units. So they are Adeline, right. So and the way you train Adeline is just use straightforward gradient descent, right, and you end up with this, okay. So people are familiar with gradient descent, right? I don't have to explain gradient descent to people. Is everyone familiar with gradient descent, right? Okay. So why am I using eta here? Step size. Yeah, why do I need a step size? Okay. So what would produce oscillations?
The line might go like that and more points might get misclassified. That happened in the case of Perceptron if you increase the size too.
Okay, great. Yeah. So let's look at it in a 1D case, right. Suppose I have a function that I want to optimize, right. Let us assume that I cannot measure the gradient properly and I am actually making estimates of the gradient, right. So I am somewhere here, right, and I find the gradient. What direction is the gradient here? That way, right. That is the way I have to change x to go up, right. And what I have to do, I have to move in the opposite direction. So if I take a large step in the opposite direction, what will happen is I will actually end up this side, okay. I will end up somewhere here, right. Now again the gradient is in that direction here. Again I take a large step, I might end up here, right? I could keep going back and forth, right? I might not actually converge. Okay, does it make sense? In fact, it's even worse. I could go back and forth and I might even diverge if I am taking very large steps, right. So, that is why you have to take small steps when you are following the gradient, right. And these kinds of methods are called stochastic gradients. Why?
Changes different dimensions for it.
No, it's essentially the, so if you just think about it a little bit, right, where do these xi's come from for you? They are not from some underlying distribution, you do not know, right. So, what you are essentially doing is there is an error function which is the error function of beta on the entire input space, right. What I am really trying to minimize is the error on the entire input space, right, but I can't compute that gradient because I do not have the data distribution, I do not have the entire data set available to me, right. I only have a sample and the sample was chosen in a stochastic fashion. So, if I am trying to minimize the error with respect to the entire data, so what I am actually finding out here is some sample gradient, right. Whatever sample data set was given to me, I am finding out the gradient with respect to that sample data, right. That is one part, right. The second thing is, typically I end up doing this one data point at a time instead of doing it n data points, right. If I spoke about this in Perceptron. So, when I am doing it one data point at a time, that is essentially not even the correct computation of the gradient. Even given the data that is available to me, I am only doing it one data point at a time. That means I am actually doing some incomplete computations of the gradients, right. And if I take really tiny steps in that direction, I am hoping that on an average I will move in the right direction, right. So, if I had computed for all the data points and taken a step, then well, given the data, that is the best direction I can move in. But if I computed one point at a time, then I have to really take tiny steps so that I am sure that on an average I am going in the right direction. Okay, so that's the idea here, right. So remember this is useful for us for the rest of the class. So what is the problem with the perceptron? People remember? Right, it couldn't do something as simple as XOR, because it was not linearly separable, right. So it is not able to solve this. Is there some way you can think of solving this? Let us call this x1 and x2. Right, what should it be? So there should be -1. How do I move it to a different space? Change the basis function, right. I can't, rotating the axis will not be sufficient for me, it will still be not linear, still not be linearly separable, right. I think I said that right. So what do we do now? Too many x's on the board, yeah. So I can define a new feature. What should I define? Will it work? Times, okay, x1 into minus x2 and x2 into minus x1, okay. So now what will happen if I do the projection of this data? Okay, so where would this point go? -1, -1, -1 is it? So where would 1 go? Minus 1 minus 1. Okay, where would 2 go? Two is here, so there will be minus 1 into minus 1, there will be plus 1, okay. Then this will be plus 1 into plus 1, there will be plus 1, is it? Okay, doesn't sound very promising. What about 4? Four is also plus 1. What about 3?
Plus 1 minus 1.
Which is plus 1? 4. So where will 4 go is my question. 4 went there. 4 is what? Plus 1 into plus 1, okay. Minus 1 into minus 1, plus 1 plus 1. That is 4 goes there, right? No, this is minus 1, that will be minus 1, it's plus 1. Yeah, there you go. What about that guy? It's minus 1. Minus 1 minus 1. Huh? Are they the same?
Yes.
So you negate x2. You first negate x1 and then take the product, okay. They are essentially the same, no? See, the idea is that I want my x1 prime to be equal to x1 and not x2. Right, they are not the same, right? Okay, now tell me. Okay. So we know that you can actually implement AND using a perceptron, right?
Yeah.
You can implement a NOT using a perceptron. Okay, great. So now do this. So where will x1 prime be for 1? X1 is minus 1, not x2, so that will be minus 1, right? X2 prime will be minus 1. Okay, and what about 2? It's minus 1. No, it's not the same thing. Okay, does that make sense? So in this transformation where x1 prime is x1 and not x2, right, and x2 prime is not x1 and x2, right, where true is +1, false is -1. Right, if you do that, then my projection will be 1 and 3 will get projected to -1 -1, and 2 and 4 will get projected to the same coordinates as they were earlier in this modified space. Okay. Now is this linearly separable? Right, so now I can separate this, right, so I can essentially construct a perceptron that does that. So what have we done here? We said XOR is hard to solve using a single perceptron, but I can hook up several of them and I can solve the problem, right. So is that computable using a single perceptron?
Yes.
Yes or no?
Yes.
That's computable using a single perceptron. That's computable using a single perceptron? Huh? First one is not.
First one is computable, second is not.
Yeah, so I am just giving people a chance to change their minds.
2 for each.
Huh?
Need 2 for each of them.
You need 2 for each of them.
1 for the and 1 for the not.
1 for the NOT. Do you need to do a NOT? Can I feed in x2 to that? Can you do a NOT?
Okay, if you invert it.
How? So if I can do x1 and x2, is it sufficient in invert the weight on x2 to get x1 and not x2? You have to think and answer. Anyway, so the point is, essentially what I have done is, right, I can actually build a perceptron that can compute x1 prime, I can build another perceptron that can compute x2 prime. So take these, feed it to another perceptron which will actually compute right. So essentially we are, somebody sneezing from the other room, is it other system? Anyway, so essentially we have shown that I can actually put these perceptrons in layers and I can solve what was originally thought to be a problem that cannot be solved by perceptrons, right. If you remember, I was telling you in the beginning, neural networks are very powerful because they are all hooked up in a very complex network, right. Individually the neurons are very simple computing elements. So individually the neuron was a simple computing element, and therefore you could not find the answer to XOR, but then by hooking them up in appropriate cascades you can find a solution to XOR, right. Does it make sense? So sorry for the initial confusion on the feature transformation, but now it should be clear, right. Yes, okay, great.